And we're back at it. It's lesson 10. We are chugging along. We're about a quarter of the way through the semester, believe it or not, because we only meet 45 times. So this is lesson 10. This will help us to avoid writing limit as h approaches 0 a zillion times for the entire semester. We're going to take a look at some general principles that help us find derivatives of polynomials generally, and that will prevent us from having to write limit h approaches 0 all the time. So it's time for us to generalize. We can do this, and we'll start with a very simple theorem. If f of x is some constant c, some number, 12, -5, 14, then the derivative is 0. And this is not too difficult to see. F prime of x is the limit as h approaches 0 of, well, we take this function at x plus h, but it's always c. Then we take this function at x, but it's always c. And by golly, that's 0. That's 0. So the derivative of a constant is always 0. And that makes sense because I've been banging the drum that a derivative is a slope. There's the constant function. What's the slope of that function everywhere all the way across? 0. So it makes sense that the derivative of a constant is 0. We have previously seen that if f of x is x squared, then f prime of x is 2x. That we've seen previously. That was in one of your OYOs. But what about this? What if it's an x cubed instead? Well, if it's x cubed instead, then g prime of x is the limit as h approaches 0 of the function at x plus h minus the function at x over h. So what is that? Well, we can expand these brackets using the binomial expansion theorem that you did for like 3 days in Algebra 2 and vowed to forget. Or we could just expand the brackets with algebra a bunch of times. We get x cubed, we get 3x squared h, we get 3xh squared, and we get an h cubed. So then what happens? Well, those go away, and then this has an h, this has an h, this has an h, that has an h. So that's the limit as h approaches 0 of those will cancel, this will cancel, this drops a factor. And so what is that? Well, as h goes to 0, this is 0, this is 0, but this is 3x squared. So the derivative of x squared is 2x. The derivative of x cubed is 3x squared. Well, dare we tempt fate again? And the answer is yes. H prime of x is the limit as h approaches 0 of our function at x plus h minus our function at x over h. And through algebra that is very, very similar, we expand the brackets. An x to the fourth will cancel out with an x to the fourth, and you end up with 4x cubed h, 6x squared h squared, 4xh cubed, and h to the fourth over h. This goes, but leaves an h behind. This goes, leaves an h squared. This goes, leaves an h cubed. As h goes to 0, those are 0. 4x cubed is what's left. So you're thinking, well, that 2, that 3, that 4, betcha that generalizes, and the answer is it does. this generalizes into something that we call the power rule, named after the very famous mathematician Power. If f of x is x to the n, then f prime of x is n x to the n minus 1. Works for all the positive integers n. There's a proof in your text. It's on page 257 and 258 in the PDF. It is worth your time. Speaking of things that are worth your time, putting derivatives together is worth your time. Three things to note here. One is if you take the derivative with respect to x of the sum of two functions, so you add two functions together, you want their derivative. Well, that's the same thing as taking their derivatives separately and adding them. If you want the derivative of the difference of two functions, well, that's the same as if you take their derivatives separately and subtract them. If you want the derivative of a function, but it's been multiplied by a constant, well, that's the same as if you just take the derivative and multiply it by the constant. These two are proven in your text on page 258. It is worth your time to read it, to see how that flows, to convince yourself that it is in fact true. I will prove the third one here for you. The proof is not terribly difficult. None of the proofs are. If I'm looking for the derivative of some constant times f of x, well, that's a limit as h approaches 0 of. We do this at x plus h. We do this at x, and we divide by h. Well, that k can come right out as h goes to 0. This constant is unaffected. But what happens to that difference quotient? Well, the limit as h approaches 0 of that difference quotient, that is a derivative. And that's what we wanted it to be. So we have established the result. This is important because these allow us to string polynomials together. With the power rule and these three rules, we can take the derivative of any polynomial that we choose. So if y equals 4x cubed minus 5x squared plus 6, find dy dx. No problem. No limit as h approaches 0. None of that. Why? Because we know that a constant multiple, we just bring that there, and we just take the derivative of this thing. Power rule says that that's 3x squared. And then we're just stringing together minuses and pluses, so we can just string together minuses and pluses. This is a constant multiple, so we just take the derivative of the x squared and put it here, and we know from a couple of slides ago that the derivative of x squared is 2x. And then this is a constant whose derivative is 0. And that becomes 12x squared minus 10x, and that's it. Like that's the whole thing. That's it. A quick OYO on the same theme. If f of x is 2x to the fifth minus 5x to the fourth plus 10x minus 1999, find f prime of x and f double prime of x. And so you'll remember that's find the derivative and then the derivative of that derivative. One more quick application here. Find the equation of the tangent line to y equals x squared plus 6x plus 4 at x equals 1. We're going to find an equation of a tangent line. That's an equation of a line. How do you find the equation of a line? It's y minus a y value is slope times x minus an x value. That x value. So this thing is going to be a y value, and this thing is going to be a slope. The y value is easy to find because we just take that x and we stick it in here. This gives us y values. That's why it says y there. This gives us y values. 1 squared, 6 times 1, 4, that's 11. The slope. Derivatives give us slopes. So we find dy dx. The derivative of x squared is 2x. The derivative of 6x, well, that's 6 times the derivative of x, and the derivative of x is 1, and then this is a constant, so there is nothing to add on. Add x equals 1, dy dx is 2 plus 6, that's 8. That's the slope. That is an equation of the tangent line. That is an equation of the tangent line. You can leave it in point slope form. You can get y by itself if you like. That's up to you. If you're looking for practice, and I'm pretty sure you are, you want to familiarize yourselves with section 3.3 of the PDF, 109, 118, 130, 137, 143. Those are all questions you should be thinking about as we get ready for class. See you then.